So when we talk about a Bose-Hubbard model, uh, basically we mean about some kind of a lattice model. So the setting is that you have a regular lattice in D dimension. And when I say regular lattice, it basically means that the lattice points, they are spaced regularly. So and there can be multiple types of, like, there are many kinds of lattice based models, like Hubbard model or the Bose-Hubbard model, or recent model by my guide, which is called James Cumming Hubbard model, and so on. So in the original Hubbard model, the degrees of freedom are the spin half fermionic electrons. So the original Hubbard model that is used to explain property like magnetism and such things, and there you talk about electrons at different lattice sites and how do they interact. In the Bose-Hubbard model, the degree of freedom is basically controlled by the spinless bosons on a regular lattice, and typical examples could be typical examples could be Cooper pairs, which are going through some kind of tunneling between different superconducting islands. So like different superconducting islands, they could be thought of as different lattice sites, and the Cooper pairs, which are basically bosons, are moving from one lattice site to the another lattice site. Or you can also talk about like helium atom, which are like moving on a substrate. So you know that helium atom is a boson, and basically we talk about some spinless boson, and the setting is a regular lattice. So given this, we define the degree of freedom of the regular lattice. So we have Bi cap, which annihilates bosons on the site I, and Bi cap dagger, which creates boson on the site I. This you can like recapitulate from your regular what do you call that, ladder operator picture, where Bi dagger refers to what do you call this, creation operator and annihilation operator, and Bi dagger commutation is given by delta Ij. Okay, so that's it. Further, we define something called boson number operator, Bi dagger Bi. So this basically counts the number of bosons which are there on the site I. So on each site I, there will be some fixed or sometimes like variable number of bosons, and this you call count using this boson number operator. And if you sum over all possible I, then you will get total number of bosons in my lattice system. Okay. So in case when there are no bosons on a particular site, if you yeah, hello.
How do you define the site? What is site here? Is it a spatial point?
Yeah, it's basically a spatial point. So what you do that when I say some kind of optical lattice or something, you have lasers, and you try to like shine lasers in various dimensions, and due to that, due to which you get different potential veils at different points in the space. And these potential veils, they are like they are regular. So and in each of these potential veils, there are some electrons or something like Cooper pairs which reside. So and they hop from one site to another, and so on. So when I talk about site, I basically mean some location in a space which has this which has the wave packet for these quantum particles like Cooper pair or helium atom, in case of if helium atoms are moving on some substrate.
Okay,
is that clear?
Yeah.
Okay, so coming back to it, so this is how we define like this is our system of interest. So around I think 40 years back or something, this model was defined, very simple model. So here you can find in the Hamiltonian there are three kinds of terms. Here you have terms I and j, terms containing I and j, where I and j refer to like j is the neighboring sites for the neighboring sites for I. So here you have interaction term which allow hopping between site I and site j. So you have here Bi dagger Bj. That basically means a photon, a boson is created at site I, and a boson is created at is destroyed at site j, which basically implies that a boson has basically hopped from site j to site I. Okay. Or you can have the other way picture where a boson has been created at site j, and it has been destroyed at site I. So this is the hopping term, and the amount of hopping that is controlled by it is controlled by this term W here. So this W could be something like the amount of tunneling you can have between the various lattice sites. So if tunneling is strong, there will be various a lot of hopping and so on. But if you reduce the tunneling, then the particles will be confined to individual sites I here. So in case there is no hopping, you will have terms like this, which are predominantly. So here, this is the chemical potential term. This term mu, that is defined as del F by del N, where F is your free energy, so which basically implies that how much free energy it costs to add an extra boson in my sample. So, and you know that F equal to E minus Ts. So at T equal to 0, it just means that at 0 temperature, it means that how much energy it costs to add an extra boson, a spinless boson to my lattice. So that is controlled by mu. If mu is large, then this term will dominate. And similarly, you have a term here which is on-site repulsion. So here you don't have terms like I and J. Terms containing both I and J are this W term only. But this term, the chemical potential term, and this one, they are diagonal. Like here you have only terms containing I only. Like they are defined on each lattice site only. So it contains on-site repulsion, which is equivalent to, like, if there are some bosons on a particular site, if you add extra boson, then that boson will get repulsion from other bosons already present. And these three terms, they constitute the Bose-Hubbard Hamiltonian. So in Bose-Hubbard Hamiltonian, in summary, you have you have two kinds of term. The first term is a non-local term, and these two terms I can group together and call them as a local term, because they contain only the on-site terms only. So this is how we define the Bose-Hubbard model. The model is quite simple, but the physics that has come out of it is quite interesting. To simulate how things happen in nature and all, how phase transition occur and so on. This model is quite interesting. Like, you can have one phase where all the particles are confined in their respective lattice sites, which resembles to insulator picture, where in the insulator the electrons, they are confined in with their atoms only and not moving, while you can have a superfluid picture where the hopping term is quite dominant, and the electrons, they are quite delocalized or something. So in this case, the spinless bosons, if they are highly delocalized, then you have one phase. And if the spinless bosons, they are localized on their sites, then you have one phase. So basically, there is a competition between local term as well as a non-local term. So I can ignore mu and just talk about W and U most of the times, and you can see that the whether I will have one phase or the another will be determined by the amount of, what should we say, the which term is more stronger. So if W is stronger, then the non-local part dominates, and in that case I have superfluid phase, while in the other case I will have insulator phase, which people call as Mott phase or something. That's clear, right?
Yes.
Yeah.
So Kishore, I had one small question. Why do we need to introduce this mu term as compared to the U term? I understand the U term will disappear if there's only one boson, and if you have more than one, it will create repulsion.
Mm-hmm.
But the requirement of the mu term I could not fully appreciate.
Yeah. So
Could you
mu term comes from the fact that to incorporate extra boson in the sample, I need to bring some in. I need to work.
But isn't that what the U term is also doing?
See, the U term is what if in the case when you have just one boson, you can have the picture where there are one bosons on each of the site.
Yes.
So in that case, there will be no contribution coming from U term. But
Yeah, but you specially put the -1 so that this happens, right?
I don't understand. Mm-hmm.
I mean, you put the -1 so that when there is only one boson, the U term does not contribute. But I mean, if I were to write this model, I probably would not put a -1 then, and I would just
No. -1 is there due to the fact that each boson that experiences repulsion from other rest of the bosons. So if there are n bosons, then the nth boson will experience repulsion coming from n minus 1 other bosons.
Okay. That's why the scaling is also going n square. Okay, maybe something. All right.
Yeah. But the mu term is coming from the fact that you have to see, every time you add extra boson in the sample, you have to do some work. And at times what happens that the two boson can come to one lattice site, and in that case you will have on-site repulsion term which is coming because of U. So U is the on-site repulsion, mu is the cost of adding a boson, and W is the hopping term.
Okay.
Yeah.
Kishore?
Yeah.
I have a question. In the tunneling part, do you assume that the weightage of tunneling from between each two different sites is equal?
Yeah, often at times what you can do that make like the distance between the sites or something very what should I say different, then in that case you can have wij kind of term there which determines how much
So
time
now you have simplified it, right?
Yeah, we have simplified it. Like we have assumed that the lattice is regular and you have some kind of translational symmetry. So no matter which lattice site you go, the Hamiltonian looks the same. So that's why I have taken our W outside. Yeah.
Okay.
Yeah. So W, U, and mu, they are assumed to be like they define my lattice uniformly. So they are like up. Okay, so is everything clear, Atul?
Yeah, clear.
Okay, so this is how we define the Hamiltonian, and you can have a case where the mu is fixed, and you can have a case where the n is fixed, and like I will leave it to you to figure out, like you get different kind of ensembles. Like fixed mu case is called grand canonical ensemble, and fixed n case is called a canonical ensemble. And as we know that calculations are very easy in grand canonical ensemble than in the canonical ensemble. So typically if we have to do some calculation, we do it in the grand canonical ensemble, and using the Legendre transformation we bring back the calculation to the canonical ensemble and do the stuff. Okay, given that so now we can look at the symmetry of the model. You can see that in our Hamiltonian there are terms like where is the Hamiltonian? Yeah. So in the Hamiltonian you can see that there are terms like bi dagger bj. Here it's n cap bi, where n cap bi is also bi dagger bi. So each time when there is a bi dagger, there is a bi term with it. So you can guess that this Hamiltonian has U1 symmetry, where U1 symmetry basically implies that my degree of freedom bi, if I send bi to bi exponential I theta, where is that? 1 minute. Yeah. So if I send bi to bi exponential I theta or I phi, my Hamiltonian remains invariant. That you can see, right? Because I have bi dagger bj and bj dagger bi and such term. So the Hamiltonian that has a kind of invariance under this transformation, global U1 transformation. Yeah. But what happens that the two different phases that we get, like the one case where the W term is dominant, and in the case where U term is dominant, if you do the calculation, you will find that in one of the phases this U1 symmetry is broken, while in the other phase U1 symmetry is respected. So basically when we talk about models and so on, it's often something like race between phases based on symmetry. So you have a symmetry, and symmetry breaking leads to different phases of matter, and in one phase the symmetry is respected, while in the other phase the symmetry is not respected. And the competition between different terms in the Hamiltonian determines which phase my system will be. Okay. So I will send you the notes. You can like have a look on this and so on. Okay. Finally, you can see that the Hamiltonian that commutes with total number operator. So I define a number operator on each site as vi dagger bi. If you sum over all possible I, then you get total number of bosons. And if you look for the commutation of this number operator with Hamiltonian, Bose-Hubbard Hamiltonian, you will find that it commutes. So that basically means that this number operator, that is a conserved quantity, right? Because that's how we define conserved quantity in quantum mechanics. So if a quantity, like in classical mechanics, if Poisson bracket of a quantity is with Hamiltonian is 0, then you say that that quantity is conserved in the classical mechanics. In quantum mechanics, we say that if the commutation of that quantity is with Hamiltonian is 0, then that quantity is conserved. So here we have number operator, total number of bosons in the sample is conserved. Okay. So given that we can do something called mean field theory with this this Hamiltonian. So as you can see that I have local terms, non-local terms, and when the system size increases, doing calculation with the Hamiltonian, that becomes very difficult. And simulating simulating such kind of models even in a supercomputer is quite a tricky business. And so we have to look for some kind of approximation or something. And this part I have taken from Subir Sachdev book, the mean field theory part, and part of something which I was discussing earlier. So there is this good book by Subir Sachdev called Quantum Phase Transition. You can look in chapter 9, and that's basically a chapter on Bose-Hubbard model. So there he talks about such things in quite nice, I don't know, nice detail or something at the level of Sakurai. So we try to model our Hamiltonian using best possible sum of single site Hamiltonians. So in the mean field theory, what we do that we assume that there is no non-local term or something. So at each site I, we think that the other bosons, they create a field, and what the boson at site I sees is the effective field at site I. So there is some already present field, but the interaction of other bosons, that is taken into account as some extra interaction field at the site I. And we try to make the non-local term as local using this what you call the interaction field at the site I. But you can see that this model will not be correct if number of bosons is number of site is quite small. So if number of site increases to infinity, then only in that case you can say feel that this model will work right. But still, to get the qualitative understanding or something, this model works quite well. So you have here H mean field defined over your U term will remain same, the mu term also remains same, but for here I introduce something called psi b term, which is the interaction coming because of the because of neighbors. So in place of bi dagger, I have here psi b, and in place of bj, I have here psi b. So as you can see that now my Hamiltonian is diagonal. So I have only site dependent, I have terms which depend on the site I only. And this Hamiltonian is same on every site. Means for every you can write this Hamiltonian as sum over I, hi. That's what I meant. Okay. So now you can see that in the earlier case, I have terms like bi dagger bj. So here you have terms n cap bi is bi dagger bj, bi dagger bi, it's bi dagger bi, it's also bi dagger bi. But once I introduce terms like psi b, you can see that this term will not respect the U1 symmetry, right? So now in the case in the phase where psi b term is non-zero, I will have a violation of U1 symmetry. That's right, Bhati? So you are with me, Bhati?
He's muted. He is with you. Don't worry.
Okay. So there are two different phases. So in one phase, when psi b term is 0, we find that we have U1 symmetry. So you have only terms containing bi dagger bi. So when psi.
Can you listen? Can you hear me?
I can. Yeah, I can.
One second. What is psi b? Is it field?
Yeah. So psi b is the Yeah.
What kind of field I was? Okay, you have
Yeah.
written it.
Yeah. So I have written
Yeah.
the
Okay.
PSI-B is a field which describes the influence of neighboring sites on site I.
Yeah. Yeah.
Yeah.
Okay.
Yeah. So you can see that, you see here that when PSI-B is 0, I have terms containing, I have terms which satisfy the U1 symmetry. But when PSI-B is non-zero, then in that case U1 symmetry is broken. So I can call PSI-B as my order parameter and look for different phases as a function of PSI-B. And in the phase
But
where
Kishore, I have a small question. PSI-B is a field, right? It's not a number, is it?
yeah, you can have a scalar field which is like uniform for the lattice.
But I never thought of fields as a number. I mean, they're
So,
always
so
operators acting on something, I thought, but okay.
fields are something like which are defined on every space time point, and they are function of a space time point, and then each space time point they are just a number. Now you can have a field operator also when you talk about quantum field theory or something, but
So
generally
they're
when
not
we talk about,
operators just now. That's what you're
no,
saying. Okay.
they are not operators. They are just like
Acha, acha.
numbers defined on the each lattice set. And since I talk about regular lattice, when I say psi-b equal to 0, it's 0 everywhere, and psi-b is non-zero, then it's regular, it's non-zero everywhere.
Okay.
Yeah.
Non-zero constant.
What?
Is it non-zero constant?
Yeah. So non-zero means in the non-zero it can have different values, depending on how much you want to destroy the U symmetry. What?
Yes, I can't get it. Is it dependent on I and j, or is it uniform all over?
It's uniform all over. Since I talk about the regular lattice, and I say that W is same between, because you can see I have introduced psi-b term coming from WVJ. I have replaced W into VJ by psi-b, right?
Okay.
So, yeah, and since I assume that my regular lattice is regular, that basically implies that there will be the neighbor that one lattice point sees is same as what other lattice point will see, right?
Okay.
Yeah. So I replaced that by this term psi-b, and you can look into that book also. He very beautifully talks about the meaning of psi-b and so on. So this is how we define the mean field Hamiltonian, and you can see that it's so beautiful that in one case when psi-b is 0 you have one phase, while in the other case if psi-b is not 0 you have another phase. And this is how we exploit the beauty of symmetry to take into account of phase transition and so on. So this is what I wanted to talk. I think it's already 5:30, 6:31 as per Singapore time. I think if you have any question or something you can ask, or yeah.
Okay.
Yeah, there are something which I can talk. What? No, I think it's done. Yeah. Yeah. Yeah, over to you, Atul. How can I remove this screenshot?
Stop sharing the screen. Yeah.
Yeah, okay.
बढ़िया है. Atul's mic is off.
Atul?
His mic is off. Microphone.
तब तक बातें तो हिंदी में बोल ले.
चुप कर साले. और बता कुछ नहीं ताजी.
नहीं ताजी क्या है, मतलब काम चल रहा है.
फेज ट्रांजिशन पढ़ रहा है.
फेज ट्रांजिशन नहीं है, मेरा काम सुपर कंडक्टिंग क्यूबिट पे है, लेकिन ये सब ऐसा ही कर रहा हूँ. इट्स बैकग्राउंड थिंग. कूपर पेयर, हाँ मतलब वो कूपर पेयर पे ही काम है.
बढ़िया है.
Yeah, लेकिन काफी इंटरेस्टिंग है. The way Topi taught us. I should not talk this thing.
क्या बोल.
अच्छा, चलो, okay, all right.
बोल दे.
अब भाटी मत
देखिए मैं बोल
परेशान
रहा
कर रहा है
हूँ
बेचारे को, छोड़
मैं
दे
बोल रहा
उसको.
हूँ कंडेंस मैटर इज वेरी इंटरेस्टिंग लाइक
Yes.
इट्स हाईली बहुत मजेदार है. Yeah.
चल ठीक है, brilliant. All right, thank you Kishore for that presentation. For your reference, on the website, the presentation he was using is already uploaded, so you can look at it if you
Oh.
like. Right. Okay, and now we'll go on to the next section, which is the research section. So I will now present my I'm supposed to do here. So I think it will be of interest to everyone. And let me just get started with it. Okay. Slides.
Yeah.
No, I can't see.
Can you see it now, Bhati?
No,
Yeah?
Bhati, you are blind.
Still can't see it.
no, I can see Kishore, not you.
Oh, okay, hold on. I think no, but I am presenting. How is that possible? I don't
I don't
know.
know.
Maybe.
Kishore, can you see?
Yeah, I can see it, Bhati.
No,
But
not me.
So what I'll do is
Not slide.
I'll show you can see me. Can you see me now, Bhati?
Not at all.
Okay. Why is that happening?
I don't know.
Okay. So, all right. So, Bhati, I would suggest you maybe leave the Hangout and then try to reconnect, and maybe it will get okay.
Okay, okay.
Yeah. Okay. I'll wait for you. Unmute. Bhati, can you see it now? Bhati?
Yeah, I can see.
Okay, brilliant. All right, so let's start. So this is the title of my research project. It's called Continuous Time, Quantum Cryptography and Communication Complexity.
Okay.
And the name of my supervisor, which they call promoter in this part of the world, is Professor Jeremy Rowland, right? And I'm at ULB, University Libre de Bruxelles, right? Brussels, I don't know how to say it exactly still. Right, so let me get started. Okay, so here's a very quick introduction to which you guys are already aware of, but I put it because the members of my jury will not know quantum information. They're computer scientists in general, right? So this is completely redundant for you. So just introducing the concept of bits and qubits. All right, and of course we know that we can do factorization and unconditionally secure key distribution using quantum information. So these are some of the reasons why the field is so popularly studied. And of course, we can try to understand quantum information, get a small flavor of it by asking this question. This is just the CHSH inequality written in a funny way. But say, for instance, Alice and Bob are asked to compute the functions, sorry, they're asked to output correlated answers if this function is zero. Otherwise, they're supposed to produce anti-correlated answers, right? And this function we can take to be IA dot IB, where IA and IB are inputs of Alice and Bob, and OA, OB are outputs of Alice and Bob. And these are just binary numbers. So obviously there'll be only one situation when this function will return a one, which is when both Alice's and Bob's inputs are one, right? Then the answer is one. In all other cases, the answer is zero. Yeah. So the outputs are supposed to be correlated only in one case, and in all other cases, they're supposed to be anti-correlated. In the first case, they're supposed to be anti-correlated, and in all other cases, they're supposed to be correlated. Yeah. If I stop making sense at any point, please let me know, okay? Because I cannot see anything other than my slides right now.
Yeah, sure.
Okay, thank you. So, all right. So this is the requirement. Now, classically, of course, you can say that Alice and Bob agree to always produce correlated results. Inputs are randomly given. It would mean that the probability of
Oh, wait.
getting some echo. Did you eject your headphones or something accidentally?
I switched to
Okay, Bhati, I hope you're still there. I'll continue. So now the point is that if Alice and Bob take the strategy that they'll produce correlated answers always, then there's a 75% chance they'll win. And it turns out this is the best classical strategy you can have. You can't do any better than this. But of course, quantum mechanically, you can use the EPR state and inputs as measurements along different bases in the CHSH case. And of course, you can win with a 85% probability. I say of course because I mean once you do the math, it becomes fairly evident. But just take my word for it, you can get an 85% winning probability. All right. So obviously, they're still not talking to each other. They are kept far away, and just like the CHSH case, this effectively shows that there's a quantum magic that even though you're not talking, you can still do better than what you could possibly do without using any quantum resources. And this is of course called non-locality. And now I'm saying all of this because it had to be a part of a presentation where I'm asking for funding. So on to saying that I've worked on this field, extending this to continuous variables during my summers, which was published as a paper later, and have worked on contextuality, which is a more general framework which captures non-locality as a special case. And I looked at that in my thesis, and that has been submitted to physical review letters. Right, but well, haven't made much progress after that. Okay, so now getting to quantum networks. The objective here is that we want to harness the full capacity of a quantum computer network. Right? So you can think of different quantum nodes connected by quantum channels. And now your objective is to be able to use this to the best possible. So to do that, you need at least two things, which are going to be the key focus of my project. The first thing is, of course, cryptographic primitives. So cryptographic primitives are small algorithms which, when put together, can construct almost all required cryptographic techniques. All right. So to be able to secretly communicate over your channel so that nobody interrupts, you need these cryptographic primitives to be implemented. Another thing you want to know is something called communication complexity, where communication complexity is just a measure of the least size quantified by looking at the number of bits of the message that you need to send to be able to evaluate a function f of x and y, where x is say given to this quantum node and y is given to this quantum node. Right. So that is the communication complexity problem. Now, of course, this has some relation to the capacity of a channel and so on, but we will not get into the details since it's a short presentation. Okay, so let's move on. We want to effectively make everything quantum so that it becomes more secure and becomes more efficient. And what have we already been able to accomplish? By we, I mean the community in general. Well, it is known that this classical communication complexity it's a number which has to be evaluated, and it's often not very simple to evaluate this number. So you, of course, try to do the best you can, which is bounding the number. So if you have a lower bound and an upper bound, then you roughly know where the number will lie. And these bounding techniques are what I'm going to talk about now. So on the y-axis, the numbers increase. So a larger number would mean a better bound because you're giving a lower bound. I hope that's making sense. These arrows are also like that. So this classical communication complexity is by this partition. So it's a combinatorial technique for arriving at lower bounds. It's a technique which I would explain at the time, but right now you can think of it as trying to see that if you have a message, then messages you can, so think of discrete messages, then you can put the inputs along the x and the y axis and think of a matrix inside it, where the matrix values are the outputs of the function, value of the input. I hope that's making sense. So now what you do is you're able to say that, okay, if the outputs are binary, which is just 0 and 1, then I can at each level partition this matrix into either giving a 0 outcome or a 1 outcome. And roughly speaking, this partitioning technique eventually gives you a lot of boxes, and you can count this number of boxes and find out what this number will be. All right, so that is the rough idea of what a partition technique is. And then of course there are further refinements of this. So there's something called a smooth rectangle technique, and there's a rectangle technique, and you can use these techniques to keep lower bounding these classical complexity, communication complexity. And there is something called a nuclear norm, which is a slightly different technique. In this, you have to evaluate trace of the trace of A dagger A, where A is a matrix, okay, of the same form as I described a minute ago. So things like these are used for evaluating other kinds of bounds, and it turns out these are usually easier to evaluate. But as you can see on the chart, these values are smaller. So a smaller lower bound doesn't tell you all that much compared to a larger lower bound. So these techniques are, although easier to evaluate, they do not give you very strong bounds. Okay, and quantum communication complexities fall somewhere over here. So it gives you values which are bounded below by these norms, and that is what is known. So this object is not very tightly bound, which means that we don't exactly know what is this number. And I mean, although we have defined it, okay, sorry. So this is what we currently understand. An interesting thing, of course, now is that this factorization norm, which is a slightly different version of this nuclear norm, yeah, this has a very interesting relation with Bell inequality violations. So it turns out that the classical bound on Bell inequalities can be obtained by using what is called the nuclear norm. And to get the quantum bound, you can use what is called the factorization norm. This is something quite interesting, and I haven't looked at it in detail. It's supposed to be a part of my reading in the PhD project. This is what is already known. Now let's move on to cryptographic primitives and see what is known over there. And this is actually quite interesting. Bit of history and research. So cryptographic primitives, well, let me describe one particular form of them. And to do that, I'll use Alice and Bob. And I'll say that there was a point in time when they fell in love and they were very happy together. But then due to some reason, they had a falling apart and now they can't stand to see each other. They bought a lot of things together. For instance, they bought a car and they bought a sofa. All right. Are you guys there with me, or am I just blabbering on the screen? I have no idea.
Yeah,
You're listening, right?
yeah, it's me.
Ah, okay, sure. Okay, Kishore, I think you're mute. Huh? Now you're okay. Okay, cool. So I'll go on. So now there's this particular situation where you have Alice and Bob, and they have acquired these things. They have a car, they have a sofa, and they want to do something with it. I mean, they want one person to have one, the other to have the other, but they can't see each other, so they can't even talk to each other or carefully distinguish. So eventually, they arrive at the only solution, which is to randomly distribute them. Okay, but it turns out that even randomly distributing is not very simple. And the reason is that, say, for instance, Alice asks Bob that, okay, you do a coin flip and let me know what is the answer. And then according to the answer and our pre-chosen heads or tails, we will give away the car. Okay. So now, of course, Bob can always lie. He can always say that if I get heads, I win. And if I get tails, you win. And after the coin toss, regardless of the outcome, he says, I got a head, and he takes the car. And Alice obviously knows the problem. She's not stupid. So she doesn't want that to happen. So this is a very classical problem. It's called a coin flipping problem, where you have distrustful players and they want to share a random bit. Okay. So this is a cryptographic problem, and it is not the same as key distribution. It's a different problem, because in key distribution, although you can send a message securely, you still trust the other player. In this, you don't trust the other player, and you still want to have a random bit shared. Okay? So that's the basic problem. So now let us be a little more specific about these things. It turns out that Alice already knows that Bob has a really good liking for the car, and he won't be wanting to give it up. So it means that if it was thought that heads is the outcome and Bob wins, then Alice knows that in the coin flip, Bob would try to steer the outcome towards heads. Okay, so given this information, can Alice make sure that the coin toss is not compromised? Okay, so this is called weak coin flipping. So in this, Alice already knows the preference of Bob, and she still wants to be able to ensure that the coin toss is not biased. Right? You can also have strong coin flipping, in which Alice has no idea. So for instance, let's think about the couch, and point is that Bob really likes the couch, but he never really told Alice about it. So Alice, during the coin toss, has no idea which way Bob will try to steer or bias the coin flip. Okay. So in this case, your algorithm has to be even stronger, and it's called a strong coin flipping algorithm. Right. Now I use the word bias, and it's good to define it a little bit better. So the word bias is quantified by epsilon, and epsilon is basically given as this equation, which says that the probability that Alice is able to force an outcome, okay, to whichever value he or she likes, or sorry, Alice or Bob are able to force the outcome to whichever value she or he like, has to be less than epsilon plus half. And obviously, the best you want is you want epsilon to be zero, so that the probability is half, which means it's random. So Alice is or Bob are not really able to influence the outcome of the coin toss. Okay, so this is how you define epsilon. Now, of course, we are studying this because classically coin flipping is not possible. Granted, you assume that the other player has infinite computational resources. So it's just like a key distribution. Key distribution is also not classically possible in that sense. I mean, we don't know exactly, but we always assume that the other player doesn't have infinite computational resources. Okay. So similarly here, you can, if you assume that the other player has, he also can't factorize numbers large enough and so on, then you can have an algorithm classically. But if you do not make those assumptions, then it has been shown that coin flipping cannot be done classically. Okay. So that's why quantum mechanics comes in. So quantumly, it was found that strong coin flipping can in fact be done with epsilon given by this number, which roughly becomes 0.207. Okay. And not just that, it has been shown that this epsilon must always be greater than this number, 0.207. Okay. So while it's extremely good that we can do better than we ever could classically, we can produce a coin flipping algorithm which has epsilon just 0.207. But we also know that we can't make epsilon disappear. Okay. So strong coin flipping, although it's really nice to know that you can do good, but you can't do as good as you would like. But it turns out that for weak coin flipping, you can in fact make epsilon arbitrarily small. Okay, and this is a fantastic proof. It was done, I think, about a decade ago, about 10 years, roughly. And the proof is, I think, 70 pages long, and it's very technical. Okay, so it's 70 pages of completely bizarre mathematics, and it was not even submitted to a peer-reviewed journal. So I can tell you something interesting. So the person who came up with this proof also came up with the best known explicit protocol, which is epsilon equal to 1/6. This so this protocol, so it's very frustrating that we know that you can have a protocol with epsilon which is arbitrarily small, yet we don't explicitly know how to construct the protocol. So it's an existence proof, although we don't have a construction. So the best protocol that we have is given by epsilon 1/6. And it just so turns out that the person who came up with this epsilon equal to 1/6 protocol has done a lot of work on this coin flipping problem. And when he finally wrote and completed the 70-page long proof, which says that your weak coin flipping the epsilon for weak coin flipping can be made arbitrarily small, he did not even send it to a journal. He just put it on the archive and let it be. So it was a very important, extremely important result in cryptography, but it was never published. Okay? And then after some time, I think a few years ago, I think 2-3 years ago, something like that, these people have figured a shorter version of the proof, which is just 50 pages. Well, it's quite a lot of reduction, and have eventually published it in a peer-reviewed journal. Okay? So that's just a bit of story. But the point remains that one of the main focus of my PhD thesis will be to figure out how to construct this protocol. Epsilon less than 1/6, and eventually, hopefully, arbitrarily small. Okay. So, as I said, this is going to be the target of my project, and how I intend to achieve this is, when I say I mean my promoter and me, because he is the one who has all the in-depth knowledge about all of these things. So his idea is to construct what is called a continuous time framework, and use this continuous time framework to find better bounds for communication complexity, and to also construct the cryptographic primitive, which is the weak coin flipping primitive, using this. Okay? So that is the main idea. So let me describe the continuous time framework to you. So usually you have discrete time frameworks. Discrete time frameworks basically mean that there is a sequential information flow. So for instance, Alice first sends some information to Bob, and then Bob receives that, does some computation on his own, and sends a message back to Alice. So this is a discrete time protocol. Okay. A continuous time protocol, on the other hand, is where you have a messaging system, which is this scheme is introduced by us. Introduced meaning we have to work on it, but this is the idea that you have the Alice, message, and Bob system separated. But now what you do is you allow them to with each other and you let them be continuously coupled. Okay. So how you do that is that you write a Hamiltonian, and this Hamiltonian has an Alice part, which is given by HA. So Alice does some computation on her own, and this Hamiltonian is not bounded. Okay. So why I'm saying that is because you can imagine that if you allow this HA to be arbitrarily large, then Alice can do any computation in time. Okay. So this is basically saying that quantifying the fact that Alice has infinite computational resources. Similarly, one can say the same thing for the last term, which quantifies the fact that Bob can do infinitely complicated computations in almost zero time. So HA and HB are written like this. The interaction terms which are given by the thunderbolt in any realistic situation should be bounded, which means that it should take some time for the message to go from Alice to the message system, and similarly from Bob to the message system, and vice versa. Okay. Now, it's quite evident that the continuous time protocol contains within it the discrete time protocol, because in the discrete time protocol, all that you're saying is that at any given point in time, term, at least one of them is zero, right? Because you're sending the message from Alice, okay, in this case, from Bob to Alice, which means that there would be a Bob sending a message. So this HMB term will be non-zero. This will be zero. Once the message has reached in this HM system, so this messaging system, then you can send it from messaging to Alice, and then it would become HAM. And in that time, HMB zero. Is there a question? Sorry,
No, it's
Can you hear me, Atul?
I think Bhati, I can barely hear you. You're very faint.
Hello.
Bhati, I can barely hear you. You'll have to be louder.
बाटी खा के बोल.
Hello. Can you hear me now?
A little better. Tell me.
Can you please repeat what is HAM and MB?
So these are, I'm sorry, my mistake. So the I, when I write I, it's just identity matrix. It's not written in the best way. Fine, I'll improve that.
HAM.
And H is just a Hamiltonian. Okay.
No, sir.
So HA would mean a Hamiltonian which Alice applies locally. HB would mean a Hamiltonian which Bob applies locally. HMB is a Hamiltonian between the messaging system and the Bob system. Okay, and you do nothing to the Alice system. Similarly, HAM would mean that there's a Hamiltonian between the Alice and messaging system identity. So that's the second term. So
Atul,
does
so
that
what
answer your
does
Yeah.
question?
Okay.
Atul,
Okay.
so what
Yeah.
does HA and HB like physically correspond to? Like HAM and HMB can, like, I can think of as interaction with the central device which sends information to Alice and Bob. But does HA and HB mean some kind of, like calculating what random number to send or coin flip or something?
Yeah, so I mean, it's since I'm not just describing a coin flipping, it's possible that, so just like any communication, it's possible that I want to do some computation computer before sending it to you. So for instance, I want to make the presentation before I send you the presentation. So making the presentation will be encoded in HA, and sending it to you would be first encoded in HAM,
HM,
and
yeah,
then consequently in HMB,
HMB,
so that you finally get it. And then
HB.
you can say the presentation is good or bad using your HB Hamiltonian.
Yeah. Mm-hmm. Mm-hmm.
Okay. Yeah, so that is the idea. So now this continuous time model can be already contains within it the discrete time model. So which means that is more general than the discrete time protocol. Okay, what is happening? I think Bharti's computer is doing something. Hey Bharti, I'll mute you, huh? You just unmute yourself when you have to.
Okay.
Okay. All right. So now we're getting back. So this, let us see how this continuous time protocol has anything to do with communication complexity. Okay. So now, as I have already preempted this, if you bound the interaction Hamiltonians, HAM and HBM, then you can say that the time required for the system to evolve to the desired state, communication complexity. Okay. So if you have the node and network picture, then sorry, node and channel picture in the quantum network, then you can always think of this as you want to arrive at a final answer, say fxy, all right, and you want to see how much communication you had to do. That in this particular framework, the way we've defined it, you just have to evaluate how much time it will take for the system to go to the desired state, and the desired state would be fxy. Okay. All right. So the advantage of this is that the very structure of this construction is algebraic instead of being combinatorial. Okay. Combinatorial is a structure which arises naturally if you're doing sequential communication. So if I send you something and then if you send me something else back, it becomes combinatorial, because for every option that you have to keep track of all the possible inputs you could have. So it grows exponentially. Whereas in this case, you're looking at a structure which is algebraic in nature, this Hamiltonian evolution. And I do not have complete understanding of how these two will be related. It's clear that algebraic objects are easier to bound. This has been known from the graph that I showed you earlier. People have done a lot of work, and algebraic bounds are easier to obtain compared to combinatorial bounds. So it's possible that if you can rephrase the problem as an algebraic problem, then the bounds that we get will be better in terms of being larger and in terms of being tighter. Okay. All right, we already have preliminary results, which is to say that we have been roughly able to show that a problem called quantum query complexity, this problem has already been characterized using a continuous time framework. Okay, this is done by my professor and one of his PhD students or postdocs, I'm not very sure. But yeah, so this has been achieved. And quantum query complexity, of course, I should tell you what that is. So quantum query complexity is that, say for instance, you have to evaluate some function, and you have a black box. Okay, so to be able to evaluate this function, how many times you had to invoke the black box is roughly given by the quantum query complexity algorithm. Okay, so this has already been done. So it's not that we're just talking in thin air. There is reason to believe that it will work. Okay, next is this continuous time cryptography, of course. So we will start with looking at the weak coin flipping algorithm, which I already described to you, the requirements of it. And the advantage is that this problem has been open for about a decade, okay? And that's after proving that made arbitrarily small. I mean, I can understand until then people were just trying to figure out if at all it's possible, but it's been proven for about 10 years that it is possible, and we still don't have an answer. And this continuous time approach is likely to give us an answer, since it's a completely different way of looking at things. But again, we have preliminary results. It's not that we're just saying this or speculating it. Our promoter, well, my promoter and his team have already been able to show that the best known algorithm, which is the epsilon equal to 1/6 algorithm, can be constructed using a continuous time scheme and then discretizing it. Okay, so they've already figured out how to make the best known protocol from the have presented. And not just that, they have from this algorithm obtained the insight that you can probably break the 1/6 limit by using what is called a history state. Okay, so the history state, well, I can say a few words about it. If you look at it carefully, it basically encodes the information. So this psi t, all right, so this psi t is basically supposed to be the state of the system at some earlier time, logical state of the system at some earlier time t. So at a time capital T, this state effectively encodes all possible logical states the system had until the time T had elapsed. So it has all possible logical states encoded until time T at time T. Okay, so that's really useful. And it's possible that we need all the history to be able to break this 1/6 limit. Okay, and that is the insight that we have. So here's the expected research flow. We intend to first work on the continuous time framework. We want to look at the definition of this framework more carefully, look at its properties, and be able to arrive at a relation between discrete time and continuous time protocols, which is not at the moment. From these, we would then go on to figuring out, given a continuous time protocol, how do you systematically reduce it to a discrete time protocol? Most of the systems that we are going to use are going to be discrete time. Right now, once you know this reduction, you would also want to characterize quantum communication complexity of quantum state generation. So instead of looking at the entire class of communication complexity, we would try to understand how to do quantum state generation, where instead of asking that I want to create a particular function, you ask the question, I want to create a particular quantum state. Patience by itself, if you're able to figure that out. And then, of course, you want to work on seeing if the same idea can be applied to classical communication complexity. So what you do is you take the same old classical models and you say, okay, I look at the continuous time version of this, better bounds and so on. Right? So that is so much for communication complexity. For cryptographic primitives, of course, as I said, we want to make something better than 1/6. Better than that, that will be a fantastic, fantastic result by itself. Once we've done that, then you want the optimal weak coin flipping. Optimal weak coin flipping will be that epsilon can be made arbitrarily small with the least resources. Okay, and that will be a breakthrough result if you're able to figure this out. And so I don't know if it will work, but we are going to try. It's an ambitious project. And once we have this optimal weak coin flipping, then it's already known in the literature that if you assume that the coin flipping problem is done, then you can arrive at a lot of other primitives by assuming that the first one works. It's called reduction to other primitives optimally, and we would want to then do that. And of course, since we are doing it by hand, we would know if there are ways of making it more optimal, because reductions are not always optimal. Of course, you would want to discretize it so that it can be implemented, and so on. And in the end, you would want to see if you can do cryptographic quantum communication complexity. So you don't say that, all right, what is the least amount of information you need to send? You ask, what is the least amount of secure information? Least amount of information I need to send in order for my communication to be secure also. Questions we'll look at, but that is quite late in the research flow. So in summary, we would what we have presented is a new approach to looking at open and relevant problems. And it's not that we're just speculating, it's a very promising approach because my promoter and his team have already produced very interesting preliminary results. Already shows that I'm a good match for this project and have there's a very good likelihood I will be able to in fact achieve most of the goals. And of course, we have a well-structured breakdown of the objectives into smaller achievable goals, as should be for any ambitious project. And since I'm actually supposed to presenting it to the jury, it'll end like the following. If you fund this, you would be helping in making quantum computer networks a commercial reality. And then I would thank them for their time and ask for some questions. All right. So, questions you can ask now. And I will stop sharing my presentation. Okay. Yeah. So, questions.
Atul, I was talking to you about this thing. So there is a guy here from IQC. I can ask for his slides or something. So so he was also talking something related to the case where like you have Alice and Bob, they don't trust each other. So it was like a distrustful quantum key generation protocol or something. And
must be similar.
So he has also like achieved some results in this direction or something. So like maybe I will send you his links or something, like I think. And
yeah, that would be nice.
Yeah, quite a nice guy.
Yeah, thanks. It's good to talk to high profile friends, huh?
Not
Well, good. Bhati, I'm not able to see you. I don't know. Are you able to see Kishore?
Camera is not working.
Okay.
You can't see me. So, actually, initially I was on cell phone and now I switched to laptop, so you can't see me.
अब तो नया लैपटॉप खरीद ले.
अभी देखते हैं क्या होता है.
So, Bhati, is there anything you would like to ask?
Not really, because it was just planning of your.
Yes, it wasn't very detailed. Right?
Yes. Yeah. So, but yeah, I like the way you designed all things.
Yeah, Atul, basically I like the breakdown of the problem. So like but I think in
that actually my guide helped me a lot with it.
But apart from like this thing that you have an ambitious project or something, try to have some side projects or something, so that like that's what I was kind of worried of. So like side may if you have something to work on, then it's better than
No,
continuously
no.
working on.
Atul, listen. Don't listen to him. Actually, you focus on your research, and that's how you do. Actually, whenever you work very focused.
Okay.
Yes, yes.
So, yeah, it's
Arey,
good.
nahi, the point is that to be able to get to answers of getting any reasonable answers, you have to produce a lot of smaller results on the way. So
Yeah.
what both of
Yeah.
you are saying is effectively the same thing. So you will produce a lot of smaller, interesting results, and you will anyway be focused on what you're working on. Yes.
Mm.
Okay.
Yeah.
And
So yeah.
sorry. You were saying something.
No, nothing. Just you go ahead.
Acha. Okay, so I was saying that with this, I think we can finish the session. There is not much else, so we can at least go off of air and stop the broadcast. We can stay for a little longer and talk about other things. But before we do that, I wanted to ask what is a reasonable time? Is this time all right for everyone? And the
Yeah.
second thing is that I wanted to decide on who talks next.
Yeah.
Is that time? It's fine for me. Kishore, is it okay for you?
Yeah. On
Yeah.
Sunday, it's okay. Okay for me whole day.
Okay, brilliant. So Bhati is also in, and Kishore is also already. That is nice. And I don't know. So where are okay? So we can ask the others. I'll send out an email also. So most likely we'll have the next session at the same time next week. And we want the speaker, of course, since there's just the three of us, and since two people have already spoken, I guess that leaves you, Bhati,
Yeah.
as
So
the
okay, I
speaker.
have to
So
decide.
would you be able to do it?
Yeah, because there is nothing in. I am doing a coursework actually, so I have to choose some
So that's
topic.
good. You can do the revision section if you like,
It's just
where
not
you
that.
talk about.
Okay.
Yeah, you can just talk about one of the courses that we either have done and you've looked at it in a different way, or something that we haven't done but might be interested in. So that will be really nice.
Yeah. Okay.
And Kishore can yeah. So then Kishore can present his research work next time because that he hasn't done. And in the meantime, I will try to read up something and do the revision for the session after that.
Okay.
Atul, I had this idea that uh, what I was thinking we can make a series or something in this thing, like we can start some kind of Landau
Yeah,
reading group or something.
yeah. I
So
was also thinking
because
that.
because
Yes.
because then it gets a direction, and then every time like someone of us has to read a chapter or a part of chapter, say section or something, and if we keep on going, then in a year at least we can finish one book or like half
Yeah,
of a
that
book.
that is a
So
better idea.
yeah,
I agree.
yeah. So
I
that's
agree.
like
Yeah.
a directed approach or something.
Yes,
So
yes.
so
So
what we
that
can do that
is
we can
So
keep
maybe
we can
next time we will do that.
yeah. So what we can do that 20 minutes we can keep for research, and that will be like we will not be talking every time about research because like after some time we will
Yeah.
be
Yeah.
knowing what each of us are doing. So what I propose that like so what I propose that we start this Landau series, one of the books, say classical mechanics or anything, and try to go through it. So maybe in our PhD we complete at least 2 books or 3 books.
yeah. That's a good idea. I think.
Mm.
Yeah, sure. So we can have a proper discussion after this broadcast. So at
Yeah.
least the speakers for the next time, then we can assume fixed, right? So Bhati
Yeah.
has to present something, and Kishore has
Okay.
to present his research. Okay. So we can decide on precisely what Bhati presents in a few minutes. But for the moment, let's close the session and uh, one for yeah, okay, I forgot to put myself on full screen. Okay, so yeah, so let's thank everyone for their time, and let's hope for another session by different speakers and more people. Thanks,
Yeah.
and I'll
Yeah.
stop the broadcast to this.
Yeah. Stop.
Okay.